So let's wait till 6:05 so that others can also join. And at 6:05 we'll start the session. Okay, so let's start today's session. Good evening, everyone. I am Dishada Devi, a PMRF fellow from IIT Gandhinagar. I welcome you all to the live problem solving session for Analog Electronic Circuits course week 2. So before starting the session, have you people gone through the video as well as the PDF document that I uploaded? Could you access those? Could you people access the video recording on YouTube and the document that I shared? If somebody could answer.
Yes, madam.
Okay, so yeah, then you people, if you could access that video, so next videos also. So if you if you have the sheet, then you can access us directly, or else if you can subscribe to my channel, then you will get the notification immediately after the video gets uploaded. And yeah, with that, maybe we can start with the problems for this week. So This is the first problem where the idea is to find the output if the input to the given circuit is a sine wave. So last time we stopped over here saying this is a new concept. So now we'll go through this concept. So here what happens is when you don't use a feedback network, so op-amp without feedback, it becomes a comparator. So by comparator, what do I mean? So the basic idea of comparator is in a comparator, you have some reference voltage, okay? Uh, some reference voltage, let's say it is ground. And here you will see output. Here you have VDD plus minus VDD, and here you are giving input. Now say if you give a sine wave as given as mentioned in the problem itself. So the moment you give a sine wave, what happens is this is a comparator. Comparator basically compares the two inputs, the both the terminals and the inputs, and gives the result accordingly. So whichever terminal has higher voltage, so the corresponding output would be, let's say if my positive terminal has higher voltage, the output would be plus VDD. If my negative terminal has higher voltage, the output would be minus VDD. Okay? And why it gives you plus and minus VDD? Because we know that the open loop op amp has very high gain. So the output saturates at plus minus VDD, right? So that's why the outputs will saturate to plus minus VDD. And it will depend on which terminal is at higher potential compared to the other terminal. So that's how you will get the output. Now here, if I start from this first cycle, so let me divide it into cycles so it is easier for us to analyze. So now when it is the first cycle, so this first cycle arises for the sine wave in positive terminal. So you can see the ground, the reference voltage here is ground at negative terminal. So when positive terminal sees anything above 0 voltage, your output will go to plus VDD. Okay. So here, the moment your positive terminal has voltage greater than 0, the output goes to plus VDD. Now it stays at plus VDD until you cross this 0 line. Okay, so until this half cycle finishes, your output remains at plus VDD. Then as you approach the second half cycle from here, now here see after 0 crossing, your sign values are all negative, right? So since positive terminal has lower voltage compared to ground terminal, so your output saturates at minus VDD. Okay. Then again, you follow through the same, you move to the third half cycle, and here you again cross the 0 line and your input is greater than 0, which makes your output saturated plus VDD. Okay. And then it will again go to minus VDD and it will follow through. So here basically the idea is when you use a op-amp as a comparator and you give a sine wave to it with reference ground, you see a square wave output with values saturating between plus VDD and minus VDD. Is this clear? So the output of this particular circuit is a square wave. Okay. Now here you could have set this reference in various different ways. So you could use some sort of feedback from output by using resistors, and from that feedback you could get the reference value basically. And when you have that reference value, so your sine wave will be like the output will be determined based on those reference voltages. So references are very important. And when you use those kind of feedback circuits, resistor based feedback circuits, to get square wave out of sine waves, we call those circuits as Schmitt triggers. Okay. And ideally, in a Schmitt trigger, you use a positive feedback along with resistors. Okay. So this is how a comparator works. So when op-amp does not have any feedback, you should keep this in mind that your output will saturate. It can either give you plus VDD or minus VDD, but the value will depend on what is the reference voltage that you are looking at. Okay. Is this clear to everyone? Question number 1. Okay, hope this is clear. If you have any doubts, please unmute yourself and ask. Okay. So coming to question number 2. So here in this op-amp circuit given in the figure, the load current flowing through RL will be. So we have to find the current flowing through RL. So this is I load. We have to find this current that is flowing through RL. So how do we find this current? What can we do to find the current in this particular situation? So the thing is, there must be some current coming from output, right? Op-amp's output and this R1. That particular current will flow through R2. That same current will be distributed among RL and R2. Will there be any current going inside? Yes, will there be any current going inside?
No.
No, right? So yeah, considering that there is no current going inside, so this is the way we can distribute the currents. So if we look into, okay, so what are the, um, let's say this potential over at this point is V. So the moment you know V, then you can simply write that V by RL will give you I, right? The current through this point will be um, V by RL. So this is also V. This is V naught. Here it is Vs. Here again, considering the virtual short concept, here we have V. So let's write KCL at V. So when we write KCL at V, we have V by R2 plus V by RL plus V minus V naught by R2 equal to 0, which is 2V by R2 plus V by RL is V naught by R2. This is one equation. Then if we write again KCL at, let's say I write it as V dash. So at V dash, where V equal to V dash. So here, considering no current here, so this is V dash minus Vs by R1 plus V dash minus V naught. Okay, it is R1. R1 equal to 0. So 2V dash by R1 equal to V naught plus Vs by R1. So R1 cancels. We have 2V dash equal to V naught plus Vs, or V dash equal to V naught plus Vs by 2. Substituting this over here, we'll have one thing we can do here is we can solve this and find. So here the variables were V is unknown, and also V naught is sort of unknown to us, right? Output is still unknown to us. We had to calculate output. The only value we know is Vs. This is input, this is known to us. So maybe we can calculate the values in terms of Vs. So here, rather than substituting V, what we can do is, in place of V, maybe we can substitute V naught's value. So it would be 2V dash minus Vs equal to V naught. So this, if we substitute there, so then it will become V naught by R2. R2. So here 2V by R2, 2V by R2 will be cancelled. So V by RL equal to minus Vs by R2. And we know that V by RL is IL. So that is the load current. So the load current becomes minus Vs by R2. So this is the load current that we will observe. Here it would have been if you continued with this. So first the idea was to find V naught, then find V. So from there we would have got the relation, but here by directly substituting we already got it. So both ways you can do. It's just that the first method is a little lengthier one, whereas this is a little bit more direct. So you can choose whatever you want. Okay. So Yeah, this is clear, right? So this was an easy problem, right? There was nothing much that we need to do. So now coming to the next problem. Okay, so in this problem, what will be the output voltage if the op-amp in the given figure has an open loop voltage gain of 10K and input input offset voltage is 5 millivolt, right? So first of all, let us understand what do we mean by offset voltage. So here, if you observe the figure carefully, the positive and negative terminal are shorted in their ground. Until now, whenever we have talked about op-amp, we said that op-amp amplifies the difference in the input, correct? So based on that concept, if your op-amp's inputs are shorted, that means the difference voltage at input is zero. So your output should come out to be zero, right? But due to some issues while manufacturing and while processing or manufacturing the device, what happens is when you short your input and output, both the input terminals together, that is your differential input, ideally you should get an output of zero. But practically what you observe is your output never goes zero. It gives you some output voltage, and whatever that output voltage is, we call it as it will give you some voltage. Okay, let's say it gives you um, some um, okay, maximum it can give you how much? Maximum it can give you VDD, right? So let's say it gives you a voltage of VDD. So the question arises, but we wanted an output of zero, right? When our inputs are same, we want our output to zero. So what we do, we start applying some small voltage to one terminal of our input, and we try to bring our output to zero. Okay, so whatever voltage you are applying to input, you start increasing it, and at some point, at some input voltage that you have applied, you see that your output voltage goes to zero. So this extra input voltage that you basically apply to turn off your or to get the output voltage as zero in an op-amp, we call this voltage as input offset voltage. Okay, this is why it is offset voltage, because this is extra voltage that you are applying to bring your output to zero, right? So ideally this offset voltage would have been zero in ideal case, but practically you need some offset voltage to bring your output to zero. Okay, that is the concept of offset voltage. And because you apply it in input, you say it is input offset voltage. So is this clear? What is input offset voltage? I hope this is clear. Okay, so as I mentioned, that we are applying this voltage where to one input terminal, right? So that means if I talk about what is my V difference right now while calculating the offset voltage, input difference is how much? Whatever is the input offset voltage, that is your input difference voltage, right? So here V difference would be 5 millivolts. And it is given that your op-amp has a gain of 10K. Now, how do we calculate output of op-amp? We say it is gain times difference of inputs. So that is 5 millivolt into 10K. So V out turns out to be 50 volts, right? Plus or minus, because sign is not mentioned. So this is the V out that we get. So the question arises, what is the maximum output then that your op-amp can observe? What is the maximum output that you can see in an op-amp? Let's say in this particular op-amp, what is the maximum output that you will observe in this?
Plus 15 to minus 15
Plus
volts.
15 to minus 15, right? But you are getting through calculation your output to be plus and minus 50. But you know that op-amp's output cannot go beyond plus minus 15 volt. So your actual output would be plus minus 15 volts. Okay, so this is the actual output. So now if you observe in your options, plus plus minus 50 volts was also given, plus minus 15 volts was also given. The moment you calculate, you saw that you have got plus minus 50 volts, you would have selected option A. But here you have to be a bit logical about the saturating condition of op-amp. So that's why the option would be D. So you need to try to scan through all the options. Then you have to rule out the options, because sometimes in intermediate steps you would get some results, and those results are given in the exams just to create some sort of confusion, but it is at an intermediate step, so you need to do further calculations to get the final results. So be a little careful in these type of concepts, right? And always try to, because many times we miss this saturation idea, and we report the output voltage as we have calculated, but that goes wrong, because saturation condition has to be satisfied. So plus minus VDD, your output should always uh, come below plus minus VDD. So that is the idea. So it should come in the range from minus VDD to plus VDD only. Okay. So yeah, moving on to the next problem. So in this problem, it says which type of amplifier has an output voltage equal to average of all input voltages? Is it inverting averaging amplifier, non-inverting averaging amplifier, non-inverting summing amplifier, or inverting scaling amplifier? So first of all, do you understand these terminologies? Do you understand what is inverting? You people know inverting and non-inverting, right? We discussed it last time. We define inverting and non-inverting based on the terminals where we are providing inputs to. It is as simple as that. What is an averaging amplifier? Yes,
Output will be the average of the all inputs provided.
yes, it will be average of the all inputs. When you design this kind of amplifier using inverting configuration, it is inverting averaging amplifier. If you use non-inverting configuration, it will become non-inverting averaging amplifier. Then summing amplifier is basically output will be the sum of all the inputs. Okay, this is possible in non-inverting case only. You cannot get uh, summing amplifier in case of you can get it, but it's basically modified averaging amplifier. Anyways, and then scaling amplifier is again the similar thing. So now the question is, what type of amplifier has output voltage equal to average of all input voltages? So average of all input voltages is averaging. Definitely from name you know that whatever amplifier is averaging amplifier, it will give you the average. And if you take non-inverting averaging amplifier, the idea is you don't see the phase shift also, which is sometimes very critical. So you don't want to have phase shift. So that's why the best suited answer for this is non-inverting averaging amplifier. Is this clear? Any doubts in this? No,
No.
right? It is very straightforward, right? There is nothing complicated in this. Okay. Now let's start with the problems this time. So, okay. In a differential amplifier, CMRR can be improved by using an increased different values are given like emitter resistance, collector resistance, power supply voltage, source resistance, etc. Right? So, first of all, the question arises that we have seen the differential amplifier. Till now, we understand a differential amplifier by a triangle, right? A triangle with two inputs and one output. We call it a differential amplifier. But actually, how an differential amplifier looks like, the design of a differential amplifier, if I have to draw the most simplest circuit, so I would draw it like this. Okay, so this is BJT based. This is a BJT based differential amplifier where you have BJTs as your operating this operating devices. Your operating devices are BJT based. Now here, when we say differential amplifiers, so yeah, maybe I'll quickly draw the MOS based also. The idea remains same, the concept remains same, everything remains same. It's just the behavior is slightly different because we are using two different types of devices. One is a MOSFET, another is a BJT. Other than that, everything remains same. So yeah, this is NMOS based. Okay. So also the thing is we have two types of most like differential amplifiers, fully differential amplifiers and partially differential amplifiers. Fully differential amplifier, so any differential amplifier for that matter will have differential inputs. Now, fully and partially differential amplifier, the term depends on what type of output it has. So let's say if I have two outputs, okay, two outputs, VO plus and VO minus, let's say, and I take the potential difference to get my V out. So here I have two outputs, two output terminals, and the difference between the two will give me the output. So this is a fully differential amplifier. Whereas if I only have one single output, V out. Okay, I only take single output from the op amp or the differential amplifier. We call it a partially differential amplifier. So this is MOS based. differential amplifier. So here the question is, we have to improve CMRR. So we already know, right? We discussed last time what is CMRR. So CMRR is the ratio of differential gain over common mode gain. Now, if you have to improve CMRR, you can either increase your differential gain or you can reduce your common mode gain, right? And by looking at the parameters, you can see it talks about emitter resistance, collector resistance, power supply voltage, and source resistance. So, since most of the uh, we have options based on BJT based amplifiers, since emitter and collector both have been given in the options, we consider the BJT based amplifiers, BJT based differential amplifier. And in BJT based amplifier, the formula for differential gain is minus GM into RC. Okay. The formula for differential gain is minus GM into RC, and formula for ACM, that is common mode gain, is minus GM RC 1 plus 2GM into RE. Okay. So this is the formula for AD and ACM. Now here when we write CMRR, we'll get minus RC by minus RC upon 1 plus 2 RE. So CMRR is 1 plus 2 into RE. So here we can clearly see that as we increase our RE, the emitter resistance, our CMRR will also improve. So the option is increasing the emitter resistance will improve our CMRR. Now, if we talk about where does this RE comes in picture, so we can say this RE will come somewhat over here. Or in this case, it would be source resistance, so RS would be here. So here we will have RS, and here we will have RE. So this is collector base emitter, this is emitter base collector, drain source gate, drain source gate. Okay. And this is fully differential. This is partially differential MOS-based amplifier. Okay. Yeah. Right. So did you understand this? Where we
Yes,
got
ma'am. Once please say about what is fully differential and what is partially differential
So fully
differentials.
differential means, see, when we say differential amplifier, that means input is always differential. So you have two inputs, and your system will observe the difference of two inputs will be the actual input to your uh, device or your differential amplifier. Okay. The moment when we say fully differential or partially differential, the idea comes from what type of output you have, whether you have two term whether your output is differential or you are observing a single terminal output. Because when we are drawing, so how does if I talk from the triangular viewpoint, so how does a fully differential amplifier look like? So your fully differential amplifier looks like this. Okay, it has two inputs and two outputs. This is a fully differential amplifier. Now, when I say partially differential amplifier, so partially differential amplifier is the one that we always use with a single output, V out. Okay? So if you see, both are differential amplifiers. Why differential? Because their inputs are differential. The actual input is a differential input, right? But the outputs are different. Whether you are taking the output as difference of the two, or whether you are extracting it directly from one terminal. Depending on that, we are calling it fully and partially differential. Is this clear?
Yes, ma'am.
Okay. Great. Okay. Yeah, moving on with the next problem. So in this problem, okay, if you people have any doubts, please unmute yourself and ask, okay? Please don't write in the comments because I don't go through the comments in the beginning. So you can clearly interrupt me, unmute yourself and ask, all right?
Can you tell common mode gain in terms of RE?
Common mode gain.
In terms of RE, what is the formula?
So ACM, the formula is minus GM into RC upon 1 plus 2 GM RE.
So if RE increases,
Yes,
then uh,
your ACM reduces,
okay, okay.
which is basically the idea, right?
But if if common mode gain increases, then current also increases through
But
RE.
you don't want common mode gain increase, right? The major idea of an
Yes,
op amp is you want to reduce your common mode gain.
yes.
Yeah.
But current, okay, okay, ma'am, okay.
Yeah, that's why it is a bit tricky. So what happens is now from here only, if you observe that your AD, the differential gain is GM into RC, ACM is also GM into RC upon 1 plus 2 GM RE, right? Now, if you start to look at ACM only and you try to reduce ACM by GM or by RC factors, you can clearly see that your AD also goes down. And also it is a problem that what happens is in first stage of your differential amplifier, the major focus while designing is you try to reduce your common mode gain as much as possible, because you can increase the gain like differential gain in next stages using single stage amplifiers. But for common mode rejection, like common mode signal rejection, only differential system would help. So that's why differential amplifiers ideal idea is to reduce the common mode signal. After that, you can increase the gain, differential gain, but the major idea is to reject the common mode. That's why we want our CMRR to be as high as possible.
So if a common mode signal is present, then where it will go? It should go through RE only. No?
Sorry?
If common mode signal is there in the
Huh.
circuit, then it should go through RE only. No?
So you are talking about how the methods to reduce, right? So we can only reduce it through RE by increasing the RE.
No, the signal, if common mode signal is present in the circuit,
Huh.
from where it is going to go out from the circuit. If the signal is the common mode signal is present.
If common mode signal is there, you will see the impact in output, right?
Yes. How will you reduce it?
So you for common mode, see common mode, basically what happens is when you are designing a differential amplifier, the idea is if you see the two stages that I have drawn in a differential amplifier, I have drawn them exactly same, right?
Hmm.
So this is a symmetric signal, a symmetric circuit basically. And differential amplifier is a symmetric circuit. The idea is both the branches that are present in your differential amplifier, they are matched. So the transistors are have the same values, same behavior, as well as the resistors and all the circuit elements that are being used in both the branches are equal. But the problem is when we talk from an fabrication point of view, you can never get two devices of same behavior if you even fabricate them at the same time. That comes from the fabrication idea because no matter how hard you try, you can never handle the variabilities that come across the chip, across the dies, and all that. So because of those variabilities, basically you don't get the exact symmetric circuit. If the circuit is exactly symmetric and the behavior is 100% in sync with one another, then you would never get an ACM. This ACM you get because of the mismatch that appears in the transistors. So if I talk from transistor working point of view, let's say one transistor is a little faster than other. Reaction times are a little different from one another, and if the resistance values are little different from one another, all these will lead to certain behaviors because of which you would have this v naught plus and v naught minus slightly different from one another, which will give you the ACM's corresponding output. Because if everything was same in both the circuits and if you try to analyze it, you can see that v naught plus will always come equal to v naught minus. There is no way possible that you would get v naught plus not equal to v naught minus, right? Because the circuit is symmetric.
Okay.
So the idea is coming from that. Let's say there is some mismatch because that will happen. You can never avoid that. So yeah, because of that you get these ACMs, and then we try to analyze, saying, okay, considering there is a ACM, what are the factors which we can slightly tweak to improve it furthermore. That is the idea. Okay. Moving on to this next problem. So here, assuming the op-amp to be ideal, the voltage gain of the amplifier would be how much? So this circuit looks a little chaotic, right? From what we have observed previously. So it appears like there is no feedback or what is happening, whether it is positive feedback, negative feedback. So let's simplify this circuit and draw it in a way that we understand and we have observed till now, right? Always try to draw the circuits in a way that you identify them. It makes solving the problem much more easier for you. Okay, so always try to redraw the circuit according to the way you understand the circuit. Now see here, R2 is connected between negative terminal and V out. So basically R2 is your feedback resistor. R1 is here. Now what about this R3? So this R3 is nothing but it is a load resistor which is actually connected between V0 and ground. And this terminal is grounded. So now here if we observe, this is clearly an inverting amplifier. It's an inverting amplifier, right? With R3 being the load. So if you attach an R3, does it make any difference in getting the output? No, right? If R3 was present or R3 was not present, you already know that V out by V in is minus R2 by R1, right? So this is the same output that you will get even if you have your R3 present or R3 absent. Okay? So it's just to show that sometimes you need to rearrange the circuit so that it looks easier. Because analyzing this circuit is much more easier compared to what is given in the question, right? That's the whole idea. Okay, coming to the next. Okay, so in this question, it is asked a fully differential amplifier has what? Similar inputs, differential inputs, zero, grounded inputs. What does a fully differential amplifier has? We just discussed it right now, right?
Differential inputs.
It has differential inputs and also differential outputs. Here outputs were not mentioned, but still it will also have a differential output. Okay? All right. Let's move to the next problem. So in this problem, what is the transfer function for the given practical differentiator? So we have to find the transfer function for this circuit given. So how we find the transfer function is whenever there is a C, a capacitor, we replace it with 1 upon Cs. When we have an inductor in our circuit, we replace it with L into S. Okay? And just we need to do that, and we will analyze it similar to normal resistors only. We won't do anything different here. Okay? So now if we start writing the transfer function, see here we have 0. So this 0 will be here, and we will write KCL at 0. So this is 0 minus Vi upon R1 plus 1 by Cs plus 0 minus V0 upon R, 0 minus V0 upon 1 by C1 is equal to 0. So it is Vi upon R1 plus 1 by Cs equal to V0 1 by R plus 1 by C1S. So V0 by Vi equal to So we can further simplify this. This is one way of solving the transfer function. The second way of solving the transfer function is just simply consider this combination, that is the parallel combination of R and C1 as Z1. Consider this series combination as Z2. And here if we see, maybe I'll draw it like this. This is Z2. Here you have Z1. This is V out, Vi. So V out by Vi is minus Z1 by Z2, correct? So from function V out by Vi is minus Z1, that is R parallel 1 by C1 is by Z2 is R1 plus 1 by CS. By using both the methods, we will get the same results. Okay? So we can use either of them.
Minus Vi.
Sorry?
It's minus Vi.
Minus?
Vi.
Yeah, it is V naught by Vi equal to minus Z1 by Z2, right? So minus will be there.
In previous one, it is minus Vi.
So I write my starting
Okay,
point from here.
step,
I have written. So it's just my way of writing KCL. You can use whatever convention you feel like, but just use one single convention, because the moment you start mixing the conventions, you'll start facing issues. So you follow your convention. This is my way of writing KCL. Yeah, so the final answer will come out to be yes, minus SRC upon 1 plus SR1C plus 1 plus SRC1. Yes, this is the final answer that we'll get. So by both the methods, you will get the same answer, because ideally the method is same. It's just that it is a shortcut method, we can say. But the derivation of this formula minus RF by R again comes from KCL only. So both are same. Okay. So moving on to the next problem. In this problem, a special case of non-inverting amplifier in which all the output voltage is fed back to inverting input of the op-amp. What is it called? So there is this amplifier where it is a non-inverting amplifier. So you are giving input to the non-inverting terminal. You have your output. Now they say you feed your output voltage completely to the inverting terminal of your input. So when we say a complete feedback, means there is no resistive path. It is like a short circuit. So you are connecting your output directly to the input. This is the full feedback situation. So in this situation, now what will happen if this is the circuit that you have? What is the potential at negative terminal over here? What will be the V? Yes, what is the V?
VI.
V is again VI, right? Considering the virtual short concept. So
It is
V
voltage
equal to Yes,
voltage
V
follower.
equal to V in. So, and V is also equal to V out. So basically V in equal to V out. So we call this a voltage follower, or we also call it a buffer circuit. Okay? Whenever you hear the term buffer, buffer basically means a voltage follower circuit, or when input equal to output. So, okay, uh, if my input is equal to output, what is the purpose of this circuit? Does it have any purpose if my input is equal to output?
Yes, input impedance is increased, madam,
Sorry?
because of very high input impedance of op amp.
Yes.
Uh, it is used between the two circuits to avoid loading or as such to isolate two different circuits completely.
Okay, so we can say that it can be used to isolate two circuits, considering for avoiding loading effect. So one can be avoiding loading effect, which is actually the key idea of buffer. Other than that, buffers are also used to introduce delays. Because definitely when your input is equal to output, that is true, but to go through that whole system, still to get your output equal to input, it has to it will take some time. So that time basically acts as a buffer or as a delay. So this can also introduce delays. So buffers can be used in introducing delays. Okay, so these are the major concepts, but the most important idea of using a buffer is to avoid loading effect. That is the impedance matching concept that we have, to have that impedance matching and to avoid loading effect. Wherever we feel like there is a loading effect happening, we if we introduce a buffer, then that loading effect will be gone. But keeping in mind that we are definitely increasing the size of the circuit, so the circuit is becoming bulkier because buffer still has some transistors, some resistors, right? So the system gets bulkier, but a loading effect will be avoided. Okay. Now, looking at this particular circuit, so the question is asked, if you have this circuit with the feedback, in the feedback path you have a capacitor, and in the normal forward path you have a resistor. So what type of circuit is this? Is it a summing amplifier, precision amplifier, differentiator,
Integrator.
integrator, right? So we definitely know that it is an integrator, but if we want to solve it, we can solve it also. So it's again, so the moment you have S in denominator, it's an integrator circuit. If you had somewhat like this kind of configuration where you had S in numerator, it would have been a differentiator. Okay, so that is the idea. Okay, so this particular circuit is an integrator. Now moving on to the next problem. So in the circuit of a non-inverting summing op amp, so there is this op amp, non-inverting summing op amp. So basically it has input in the non-inverting terminal with the V1, V1, V2, V3. It has three inputs. This is plus 2 volt, this is minus 4 volts, this is plus 5 volts. And the input resistors for all three input signals are same, that is of 1 kilo ohms, 1 kilo ohm, 1 kilo ohm. And the feedback resistor is 2 kilo ohms. RF of 2 kilo ohms, V out, this is grounded. Determine the voltage Vp at the non-inverting pin. So basically this is Vp, this is Vp, and the output voltage that will appear across your V out node. Okay, so first of all, how to solve this problem? Yes. How do we solve this problem? Now here you have multiple inputs, right? So if we have multiple inputs, then the best way is when you have multiple sources, the best way to solve the problem is by using superposition theorem. If you don't understand anything and you need to start from somewhere, so the best idea is to use superposition theorem to solve this problem. So by superposition theorem, what do we mean? So basically we mean that we will use one input at a time. Okay. Considering other inputs at ground or at zero, we will only consider one input at a time. So VP1. So now if we see that VP1, what is the value for VP1? So this is basically 1k ohm, 1 kilo ohm, 1 kilo ohm, ground. At this point you have VP1 and here you have plus 2 volts, right? This is the circuit. So how much is the VP1 that we observe? It is 2 by 3 volts, correct? It's 2 by 3 volts, right? Any doubts in this?
No, ma'am.
Yeah, okay. So if this is VP1,
Can you explain 2 by 3?
2 by 3 is basically coming from here, right? It is 1K. 1 kilo ohm. This will give you 0.5 kilo ohms. This is ground. You want to have the potential over here plus 2 volts. So VP1, what is VP1? VP1 is 0.5 by 1.5 into 2, right? So that is 2 by 3. Basic voltage division.
Okay.
Yeah. So this is VP1. So first part. Now for second part, okay, for the second part, we will put this to ground, and here we have minus 4 volts. So again, and this is VP2. So VP2, the equivalent circuit will look like 1 kilo ohms. This is minus 4 volts. And here again we have ground, 1K, 1K. So your VP2, this is VP2. VP2 again becomes minus 4 by 3 volts. Right? So this is part 2. Now when we talk about part 3, considering the third input, this is grounded, and here we have plus 5 volts, and this is VP3. So the circuit for VP3 would look like, again same circuit, plus 5. So VP3 will become 5 by 3 volts. So the final VP potential will be 2 by 3 minus 4 by 3 plus 5 by 3. So 7 minus 4 by 3, that is 1 volt. So the final VP, or the potential that you'll see across this point, is 1 volt. This is 1 volt. So always it is advisable, whenever you have multiple sources, you go for superposition theorem. That is only analyzing one source at a time, and then merging the effect of all of them. So adding all the impact of all the sources, and you will see the effect. Okay. So yeah. So VP is 1 volt, and input resistances are all 1 kilo ohm likha hai. So considering this also to be 1 kilo ohm, then we will have V out is 1 plus RF upon R1, let's say this is R1, into VP. So that is 1 plus 2 by 1 into 1. So this is 3 volts. So V out becomes 3 volts. Right? So the idea of this question was, see, this particular circuit is not very difficult. It is an averager circuit, like basic averaging circuit. So you can directly write the formula. But the point is, let's say this circuit was any complicated, then you need to know how to analyze the circuit. And for analyzing it, when you have multiple voltage sources, you should always go for superposition theorem, because superposition theorem stands true, and that's how we analyze the complex circuits. Okay, so only see the effect of one source at a time, and then add the effect of all the sources. That will give you the final output. Okay.
For different resistors,
Sorry.
for different resistors, how to calculate?
Yeah. For different resistors, how would you calculate? So that's what I'm saying. For different resistors, your averaging formula will not work, right? There you will use this superposition theorem. So superposition theorem mein what will change? The resistance values will change. So like all these resistor values. So here, here. These values will change. You will calculate the effective resistances, and accordingly you will divide your voltage. So it's basic voltage division only. There is nothing much here.
No, in V0.
In case of V0, so V0 only depends on which resistance V0 depends on. It depends on the feedback resistor and the resistor that is this particular resistor. So this R1 is important for V0, not the other input resistors. They are not important.
Which is R1 here?
The R1 is this resistor. So this is R1. This particular resistor is R1.
Oh, okay.
So this is the resistor that we are talking about, okay?
Okay.
So be it inverting configuration or non-inverting configuration, the two resistors which are important while calculating the gain are RF and R1 only. So the resistors in the square box, enclosed in the square box, are only taking part in the gain calculation. Other resistors are not playing any role. But here the voltage that we use in calculation is VP. Okay. Output calculation may this VP is calculated.
Okay.
Yeah. Is this clear? Okay.
Clear, ma'am.
Yeah. So let's move on to the next problem. So in this problem, it is given that this is a differential amplifier circuit with R1 being 2 kilo ohms, R2 being 2 kilo ohms, RF and R3 are both 10 kilo ohms. So what is the gain of the amplifier? Okay, so in this particular circuit, see in this circuit again, what we can do is we can apply superposition theorem and we can solve it. Okay, so let's apply superposition theorem when Vs1 is equal to Vs1 is not equal to 0, Vs2 is equal to 0. This is the first condition, right? So when Vs1 is not equal to 0, Vs2 is 0, so that means this is grounded. In that case, it is an inverting amplifier, right? So V01 will be how much? Minus Rf by R1. what we need to find? The gain, right? V0 by Vs1. So minus Rf by R1 is the gain. Now, in second case, when Vs1 is equal to 0, Vs2 is not equal to 0. Or I can write it like V01 equal to minus Rf by R1 into Vs1. So this is V02. In this case, V02 by Vs2 is now, in the second case, this is the inverting configuration. So here, this voltage we need to find out. How much is this voltage? V plus. Because the final output that we will get is based on this V plus. So 1 plus Rf upon R1 into V plus will be your V out. So here this V plus needs to be found out. So V plus is 10 by 10 plus 2 into Vs2, which is basically 10 by 12 or 5 by 6 times of Vs2. So V02 by Vs2 is 5 by 6 times of 1 plus Rf by R1 into 1 by Rs by R1. And this is V02 by Vs2. This is 5 by 6. 1 plus 10 by 2. This is 5. So 6 by 6. So this is 5. Here it is minus Rf by R1. So V01 by Vs1 is minus 10 by 2. This is minus 5. So this is minus 5. This is 5. So we So considering here, the idea is that the total amplifiers situation, if we see that we can analyze it like V0 is gain times V difference. And here the V difference is given by Vs. Okay. So Vs into gain times V0. Now here, if say we consider that Vs1 minus Vs2 is Vs as seen from the image. So this is Vs. So putting, because we need to take one as reference, right? Any one needs to be a reference. So putting Vs2 to ground. So that is Vs2 is 0. So Vs equal to Vs1. And if we have Vs2 to ground, then Vs, which is Vs1 has a potential of Vs, and this is an inverting configuration. So your output gain becomes minus Rf by R1, and output becomes minus Rf by R1 times Vs, which is the potential difference. And this minus Rf by R1 is how much? It is minus 5. Okay. The thing is here, we could have again gone for superposition theorem, but you can go through that way also, you will get the answer. It's just that since Vs1 and Vs2, the absolute values are not given. So if the absolute values are not given, so we can consider the difference as Vs, and considering 1 as reference, if we solve the gain, we'll directly get it as minus 5. Putting other to ground. This is because here we are considering 1 as reference to the other, and we are considering the difference of 2. Okay, so otherwise, if the values were different and values were given, we could have calculated both the values through superposition theorem, as we did in some question, right? Yeah, in previous question we did that. Now in the coming question also, here again it gives a similar kind of flavor. So here it says that Vs1 is a 3-volt signal and Vs2 is a 3.3-volt signal, and we have to find the output. So here 2k, 10k, 2k, 10k, right? And we have to calculate the output. So here if I write, so from direct calculations, V out is AD times V difference, correct? So V out, if it says minus 5 into V difference, so earlier as we have taken the difference, in the similar way if I consider the difference, so it was Vs1 minus Vs2. So likewise here it is 3 minus 3.3. So which gives me a V naught of 1.5 volts peak to peak, right? Now the same thing, let's say if I do by using what we have is superposition theorem. Okay, by using superposition theorem, because solving a superposition theorem becomes much easier when you have the values in hand. That is the only thing. So by using superposition theorem, for Vs1 equal to 3 volt, V naught is minus Rf by R1 into Vs1, that is minus 5 into 3, which is minus 15 volts. Now second, for Vs2 equal to 3.3 volts. So if Vs2 equal to 3.3 volts, then this V plus needs to be calculated. So V plus is 10 by 12. 10 by 12 into 3.3. And V naught is 1 plus Rf by R1 into V plus. So that is 1 plus 10 by 2 into 5 by 6 into 3.3. So here we have V naught 1, V naught 2. So V naught 2 is 6 into 5 by 6 into 3.3. These two cancel. So 3.3 is how much? 16.5 volts we are getting from here, right? And here we got 15 volts as V01. So now V01 plus V02 is V0, correct? V out. The final V out is the sum of two outputs. So this is 15 volts plus 16.5 volts is V out. Minus 15 plus, here it is minus. So minus 15 plus 16.5 is V out. So V out is 1.5 volts, right? So 1.5 volts is the final output. Now by using the same method that we did last time, like in the previous question, we again got the same values, correct? It is 1.5 volts. Here the only thing that we did is like, yeah, so here, if we go by this long way of solution and substituting it again, then Vs, uh, so it is like, it was V01 is minus 5 times Vs1 and V02 is 5 times Vs2. So V0 is V01 plus V02, that is minus 5 Vs1 plus 5 Vs2 is V0. But since Vs1 and Vs2 both were unknowns, so from here also, if you see that minus 5 Vs1 plus 5 Vs2, when you substitute the second, and when you try to solve the second question output by this, you will get the final value of 1.5 volts. So superposition theorem is valid. The only difference that we did here is, since Vs1 and Vs2 both were unknowns to us, we took one as reference. So we said that let's Vs2 be 0, and the difference between Vs1 and Vs2 was known as Vs. So we used that and then we found the gain. And by using that gain, when we multiply it with the voltage differences, we get the output. By using the superposition theorem also, we get the output. Superposition theorem, I understand sometimes it gets a bit lengthy because you have multiple sources or basically multiple sources are there. These multiple sources lead to a lot more calculations, but you have to be a bit patient because at the end of the superposition theorem, you will never get a wrong result. It will give you a right result. It's just that it becomes a little lengthy. But if you don't understand what to do, like where to start from, you have too many sources, the best idea is to go for superposition theorem. You can simplify the circuit a little bit, then apply superposition theorem. It's up to you. But in multiple source cases, superposition theorem always works. So that is my honest suggestion. That's why I solved like last 2-3 problems using superposition theorem, highlighting the importance of it, because sometimes it is very helpful in using superposition theorem. Even in future, when we will have both AC and DC analysis to do together, there also we will apply superposition theorem. Like first we will do DC analysis, then we will do AC analysis, and then we will add both the results and say this is the final result. Because it is very tricky to analyze both AC and DC together in a circuit. So in many places we take help from superposition theorem. Okay? Yeah. So moving on to the next problem. So in this problem, it says that the input offset current equals what? So in the beginning of today's session, we talked about input offset voltage, right? Input offset voltage was the voltage that was required to bring your output to zero. When you have a balanced or shorted output, what is the extra input signal that you require to bring your output to zero? We call it as input offset voltage. Similar to that, your input offset current is, see, again it says input, so you know that it is for input, and it is talking about the currents. But we know that in our op amp, we say that input currents are zero, right? V out, V1 and V2. We say the input currents are zero, but there is a possibility that there is some current that flows through these two. So say I1 and I2. So in case of MOSFET, these currents are zero because it is the gate current. In case of BJT, I1 equal to I2. This should be case. This should be the ideal case. Okay. So both the currents which are going in BJT based op amp. Okay. In BJT based op amps, the biasing currents of both the BJTs I1 and I2 should be equal, such that I1 minus I2 comes out to be 0. Okay. But if I1 is not equal to I2, such that I1 minus I2 is non-zero, so whatever is the I1 minus I2, we call it I offset. Okay, so this is the offset current. So the difference between the I's is I offset current. Okay, when you have same voltages applied, let's say both are grounded. If both the terminals are grounded and there is current flowing through both the transistors, especially in BJT, the current will flow. In MOSFET, the current will not flow unless it has seriously some leakage current going on. Otherwise, the currents will be zero. So, or equal. So, if they are not equal, and then you see the difference between the two input terminal currents, that difference in the input terminal currents is your offset current, input offset current. Okay. So here it asks you what is the input offset current? Is it a difference between two base currents, average of two base currents, collector current divided by the current gain, or the sum of two base currents? So the answer is it is the difference between the two base currents. So the input offset current is the difference between the two base currents. Is this clear to everyone? Any doubts in the offsets?
No, ma'am.
Okay.
No, ma'am.
So these were all the problems which I had kept for today. But other than these, if you have any doubts, feel free to ask, since we have some time left with us before we can end the class.
Please explain about the assignment problems, the way of approach to we have to address, where they show some current source which I never seen before.
So you're talking about this time assignments. Unfortunately, we cannot discuss the assignments which are posted this time. We are not allowed to discuss those problems, so that's why we cannot take up the problem. But if you need some like help regarding any concept, maybe we can discuss. So what type of concept? Do you have any doubts in any concepts or anything which is given in the question that you feel like it was never addressed? So maybe you can ask that. I can discuss that concept if you want, but I cannot take up the problems. These are strict instructions from NPTEL. So yeah, that's where I cannot help. If you feel like there is some concept that is missing that you don't know, I can help you with that.
Ma'am, can you explore the concept of stability of an operand?
Okay, so stability, it's a huge topic in itself. It's not as easy as possible. But to briefly explain, so see, when we say stability, we talk about the stability in terms of mm, pole position in frequency responses. So from here, you basically, where your poles are placed, based on that, you will get the phase margin. And this phase margin tells you the stability. Okay, so this is the idea. So, okay, so it's a bigger problem. So do you want me to like go through the stability concept throughout? Or like, so based on phase margin and everything?
Yes, ma'am. If you have no problem, then you can
No, the
explain.
only thing is that it is a bigger problem and it consists of a lot of things. But maybe I can simply um, discuss it very briefly based on this, starting from the phase margin problem, based on the phase margin and discussing how things are related to phase margin. So, based on phase margin, maybe I can take it up.
Okay, ma'am.
Yeah, so just. Phase margin. Okay, I'm looking into actually, I have one good notes for the stability, so I just want to follow that. Meanwhile, if somebody has some other doubt, you can feel free to ask. Do you have any other doubts or any other concept that you want me to discuss? Or are there any concepts like the submission is approaching? So, are there any concepts in the assignment that you feel they were not taken up in the like the lectures? Was there any concept of that sort that you want me to discuss?
Madam, will we have any class or tutorial like live session on
Sorry?
the will we have
Huh.
in future
Huh.
any tutorial based on the assignment which are provided already?
No.
Discussions on the problems
So the problems
in the
which are
assignment.
provided to you, you will already get the solutions to that. The moment your submission is done, the next thing that you know is you get the solutions for them.
Okay.
So there is no need to discuss it again, I guess. But still, if you feel like that there is some solution that is given that you don't understand, maybe we can take up that. But yeah, you will get the solutions.
Okay. Okay.
Yeah, yeah. Where did it go?
Ma'am, how to find the order of the transfer function?
Order of transfer function is number of poles that you have.
Okay, see, if my system has like this 10 plus 10 of s plus 2,
10 of?
s plus 2
Huh.
divided by
Okay.
s into s plus 1, s into s plus
Okay.
1,
Huh.
plus into s plus 3 whole square.
S plus 3 whole square.
Yes, ma'am.
Okay, so it is basically a 4-pole 1-0 system.
How do you tell, ma'am, 4 pole?
Because there are 4 poles, no? 1, 2, and here you have 2 consecutive poles.
But here it is written order of the pole is 2.
Order of the pole. Okay, because the thing is, when you have zeros also, so one considering that one pole compensates 1-0.
Okay.
So if you neglect that, then you are what is the remaining one? So it's like if there is no zero, then the order of the system would have been 4. But now since there is, so एक second, what is the order of the system? Is it 2?
Yes. So, pole has an order of 2.
So this was in the solution.
Yes.
The order of the system is 2.
Uh,
What would it be 2?
so can you tell the poles at which location?
So here if we see that one pole is at 0,
Uh,
another pole is at 1, there are 2 consecutive poles at 3. So 0, 1, 3, and then there is this 0 which is 0.2, which is at 0.2. So here very close by you have a 0.
hmm.
This is the situation. If I consider that these two compensate each other, still you have 3 poles and the order becomes 3. Why is the order 2?
It's
So
not
it is
written.
like, see, how you find the order is you have a transfer function, right?
Hmm.
Numerator and denominator.
Hmm.
So in numerator, you have, let's say, s to the power n is the highest order of s.
Hmm.
Okay.
Hmm.
And in denominator, you have s to the power of d. Okay.
Hmm.
So what you do, you try to divide your numerator and denominator based on whatever is the lowest of the two. Let's say n is less than d. So what I'll do is I'll divide s to the power numerator by s to the power n, whole of numerator, and also whole of denominator by n, s to the power n. So the order of the system will basically become s to the power d minus n. So basically order is d minus n. So this will be the order of the system. Because since we will have pole dominant systems majorly, so yeah, the order of the system should be d minus n. So according to that, the order of your system should be 3, but is it because you have poles at the same location? That's why it is. Multiple poles will not be considered. But ऐसा तो नहीं होता है. Order of the system. Maybe I'll look into this. And just in case you also look into this order of system concepts once online.
Okay.
Yeah, because generally how we define the order of system is the highest order of S that is left. So after nullifying everything, so what is the remaining order? Based on that, we tell ki order of the system is this much, um, and which basically translates to how many number of poles are there. So here also, that's why I said if I nullify one pole 1 0, I should get 3 as the order. But I'll look into it once. If your answer is 2, the most probable reason could be that one pole and 1 0 are already compensated, and another pole is like pole location is same. So if you see, there are 2 poles only, but the frequencies that you get out of your system are 2 only. It's just at one frequency you have multiple poles, 2 poles, but number of frequencies you are getting are 2. So that's why the order is 2. But yeah, I need to look into this once.
Okay.
Yeah, maybe you
And
can also look into this
okay.
for order. Yeah.
And you always consider peak to peak in this one, or only peak voltage in AC?
In AC, what for which analysis
Uh,
you want to consider?
you took peak to peak voltage.
Huh?
What if we take only peak voltage?
No, it depends. In question, if it is given peak to peak, you will calculate for peak to peak. If it is given for only amplitude, you will calculate amplitude. So it's according to the problem. What is it asked in the problem? At the end, it will come out to be same, because if you are getting some value for peak to peak, then half of it will give you for amplitude. So it will not change anything logically, at least.
So AC means we should take peak to peak.
Yeah, ideally we do. We do take peak to peak.
Okay.
Yes. Mm, stability. Is any other doubts?
Can I have your email ID, ma'am? Can I sort of post the question?
So if it is related to this assignment, I cannot help you. I'm
No,
pretty.
not this assignment, ma'am. Like this, the polls. This one.
Oh, if you have any general question, maybe you can ask here only, so um, others will also have this opportunity of going through that with us, right?
Okay.
Yeah, okay. So phase margin. See, the stability, it comes from, first of all, where is the position of your poles and how close by or how far these poles are from each other. And there is a lot that goes into stability analysis. But if I have to boil it down to calculating the stability of the system, so the measure that we use to calculate the stability of a circuit is through phase margin. Okay. So phase margin is calculated as 180 degrees minus the phase of the circuit at a given frequency, because phase margin or phase of a circuit where you will calculate will depend on what frequency you are selecting, right? So phase margin is always 180 minus phase of the circuit. The higher the higher phase margin means higher stability. Lower the phase margin, lower the stability, okay? And if phase margin goes below, like if phase margin goes less than 0, then your system is unstable. Okay, this is the measure used for stability from a calculation point of view. So for calculating and quantitatively justifying the stability of the system, we define the phase margins. Okay. And yeah, somebody was asking some question, I guess, before I started with margin. Yes. What was the question? Somebody was asking something? Hello? Somebody had some doubt, right?
For which one, ma'am?
Sorry?
For which one? The poles.
For which one?
For, for, for poles you are asking?
Sorry?
For poles you are asking?
Holes? I did not get your point.
I think he is asking what you have explained just now. That
Oh,
is
what
a
I
pole.
explained is
That is a
related to
pole
stability.
stability. Right.
Stability.
Right.
Yeah, it's related to stability of the circuit. And in stability, you calculate the phase of the circuit and you find the phase margin. Okay. So phase of the circuit at a particular frequency, and you check whether at that particular frequency your circuit is stable or unstable. It depends on the phase margin value. And when we talk about phase of the circuit, it takes into account the poles and zeros both, because it is the phase of whole circuit. So you find the transfer function and you find the phase from that transfer function, and then you substitute the frequency values and you check till what frequencies you are getting the phase margin which is greater than zero. The moment your phase margin goes zero and below, your system is unstable. So that justifies that after that frequency, you cannot use your circuit. Or basically, your circuit is unstable. So that's how, by quantitatively, you tell which circuit is better than other, depending on the phase margin values.
Ma'am,
Yes.
may I request something that if you have any material regarding this stability or any book you like to refer, then please
Actually,
share.
I don't have a book, but I did take one lecture last time where I explained stability in various different aspects and all. Um, maybe I can take up stability in some class because stability has a lot to it. So yeah, it's a good discussion and it is one of the major topics also. So maybe in one session, I can explain stability. If you want, I can take stability in next week also, but it
Okay.
depends on you people. So do you want me to explain stability?
Sir, it will be, ma'am, it will be good for us.
Okay, so I can take up stability. So stability, it will be something around half an hour to 45 minutes discussion. I'll try to cover as much as I can
Okay, ma'am. Thank you.
in stability. Okay, so maybe I can have the stability discussion next week. And then after that, but we will be left with lesser time for problems. Is that fine? Because problems will also need to be covered, right? But stability is a good topic, and I definitely would love to take stability because it has a lot of insights and
Ma'am,
definitely.
ma'am, if you feel a short of time, then you can share if you have any material with us.
It's not like material. I don't have material as such. It's more about different lectures that I have come across. I compiled them to explain things. So
Okay.
I
Okay.
did that last time. I can
Okay.
do that now also. I don't mind doing that. So yeah, maybe I can take stability next time. Okay, or I'll look into that in which week we have stability related problems. So maybe I can take stability first, then we can solve the corresponding problems also. So that will be a better way to go ahead.
Right, that will be better, I think.
Yeah. So in whichever week I'll see that there are problems based on stability, then I can take up the stability first, then we'll go through the problems. So it will be a good flow. Yeah, I'll do that. Okay. Meanwhile, do you people have any other doubts? Is it clear? Everything? The problems today were much easier, I guess. Last week, there were a lot of concepts. In each and every problem, we had some new concept. This time, the problems were much easier. But yeah, anyways. Hope things you are able to understand what I'm trying to explain. And in any case, if you have any doubts, please unmute yourself immediately and ask. I don't mind being.
Ma'am, I have one more request that I missed your last live session class.
Okay.
So can I have that discussion or any?
But that video is on YouTube.
Okay.
The whole lecture is on YouTube. So you can, okay. So you can search my name, D. Sharda Devi, on YouTube. You'll get my channel.
Oh, okay. Just a minute. Okay.
Yeah, you can subscribe to it also. So the moment I upload a new video, you'll get the notifications also.
Okay.
Or it'll come to the feeds. Yeah. And I guess NPTEL must have shared the sheet with you people also. There also you can find the video.
Right. If it is shared by NPTEL, that will be easier for us to find it.
I guess it should be. So there you can find the PDF also, and this also, like video link also.
Okay.
That will
Okay.
be
Right.
available there. Yeah.
Great. Great.
And also, if you can subscribe to my channel, so like you don't have to wait to that.
Right. Definitely, we will subscribe to the channel.
See. And I guess in the video link in the description, I have tagged that PDF folder also. So you can, from there, you can see the PDFs also directly. So all these notes that I'm preparing, these will be uploaded on Google Drive, and you will have the link. Okay, if there are no other doubts, maybe we can break over here and meet next week with new set of problems and new set of concepts. Are there any further doubts? Anything you want to discuss? Okay, so if not, then that's all for today. Thank you everyone for joining. See you all next week. Bye.
Thank you. Bye.